So now we come to the alternative to explicit threading with explicit programming with threads. Actually, we can do this with threads also, but there are much better alternatives, as you will see. It's called structured programming with patterns. So patterns are so-called best practices for solving specific problems. So we know how to solve certain problems, and we call that a pattern, and that pattern can be reused on other kinds of similar problems. So patterns can be used to organize your code. It can lead to all algorithms that are more scalable and maintainable. And in particular, a pattern supports a certain algorithmic structure with an efficient implementations. And some programming models or languages support different parallel patterns better or worse. Patterns are used in any kind of programming, and in normal structured programming, you use a lot of patterns to make serial computation good. You know how to deal with sequences, selection, iterations, nesting functions, and all these things. Using these patterns, you can almost or mostly eliminate the use of things like goto and creation of spaghetti code, and the maintainability of the software is greatly improved. With structured parallel patterns, you have similar kinds of patterns that can be used to make parallel programming similarly good. You have superscalar sequences, speculative selections, map, recurrence, scan, and so on. We'll deal with several of these later on. Using these patterns, threads and vector intrinsics can mostly be eliminated, and the maintainability of the software is greatly improved. And here's just an overview of a few patterns, and we'll deal with a few of them in this course. And in particular, we're going to deal with map, we're going to deal with superscalar, we're going to deal with reduction, we're going to deal with pipeline and fork join, and probably also geometric decomposition and partitioning. But we'll see with that. Let's say a few words about notation. Green boxes here represent data. Blue squares represent tasks to execute. A black circle represents a fork in the execution path. A yellow circle represents a join, and an arrow represents a dependency, typically between tasks. So here's an example. We have a serial sequence of functions f, g, and h that has to be applied to data A here, and f uses A, produces F, that is as input as G, so there is a data dependence between, of course, the data A and the function F, but also with the function F and the function G, because of the dependence here. And similarly, the G output here is an input to function H, so there is a data dependence here, also it produces data B. So the total serial sequence is a sequence of tasks, F, G, and A, that are dependent on each other, so they can't execute in parallel. The whole sequence uses data A and produces data B. Here's an example of one of the most important and powerful patterns. That's the map pattern. So the map pattern replicates a function over every element of an index set. So the index set here is the set of green boxes here, and the map function are these blue boxes here. And what is important here is to realize that the function here is the same for all elements. So map replaces one specific use of iteration in serial programs with independent operations. So in serial programming, this is done sequentially, one element at a time, and with map you can do it in parallel. This is very, very useful kind of pattern in many kinds of operations. Second very useful pattern here is the reduction pattern. A reduction pattern combines every element with a function, certain function, and produces a single scalar element, and the function has to have an associative operator. So this example here shows how you can do this in parallel, partly in parallel reduction. You reduce the two elements at a time with the function, and then you have, of the 8 elements, you now have 4 partial reduction elements. You can combine them in total, and now we have 2, and you can combine them to the final result. And this is also very, very common kind of operation. And you may have heard that Google invented the programming model MapReduce, which essentially is a way to do map and reduce functions over a large set of elements over big clusters of computers. So the dot product, as we saw in the previous examples, is actually an example of the map reduce pattern. So we have the function, the function here, the map function is the multiplication, and the reduce function is the sum here. So sprod is called in parallel with chunks of array multiplication and calculates the partial sums, and the final reduction is done by the master thread sequentially. If we want to do this in a little bit different way, we can have a look at another parallelism that exists in most computers. That's the use of SIMD instructions. So SIMD instructions are instructions that operate not on a scalar value, they operate on a set of values. So you have typically these SIMD registers that are larger than normal registers. So the SSE registers in Intel processors, they have typically space for 4 single precision floating point values. So they are 128 bits large. So you can make room for 4 single precision floating point variables, and you can do arithmetic on these 4 values with one instruction. So the code here in the middle, or to the right on the slide, is the same code as the plain C++ code here, but with the intrinsics for using SSE instructions in an Intel processor. And I will not really well, I want to point out a few things. I won't go through it in detail. One thing is that the for loop now iterates 4 iterations, 4 times the over 4 values at a single iteration. We load here the SSE registers. We make the multiplication, and we make sum here. But then we need to do the reduction sum also somewhere around here. So this executes is about 4 times as efficient as the previous code, but the code is specific for a certain version of the SIMD instructions. In this case, SSE, it's not portable, and also it's specific with a vector length of 4, which also makes it not portable to new kinds of vector instructions. It's verbose, it's very hard to maintain. It's only vectorization, no threading takes place here. And it's not even complete because it assumes the array is a multiple of vector length. Remember, we took care of that by checking the AND iterations for one of the threads previously, but here it's not taken care of. So let's look how we can do this particular problem with a higher abstraction model. If you want to vectorize the code, okay, so here to the left you have the normal sequential code. Here to the right we have vectorized code with Silk plus array notation. Very similar to, well, very simple compared to the SSE code. We specify that we operate on array which are start with iteration 0 and are of size. So, and here is a second array. We multiply them element-wise this way, and then we have a special function called sec_reduce_add that performs the reduction to a single scalar addition. Simple, right? Still no threading, but very simple vectorization. Here is a way to do both vectorization and threading. This is also with Silk Plus. So Silk Plus is a program model that Intel promotes and which is also now part of the GCC compiler. Okay, we do the reduction here, but then we do a threading here, and we do a for loop that goes from 0 to size, as before. And then we specify that we do chunks of 4096, so that's specified here, 4096 elements that we vectorize over. So we vectorize over 4096 elements, but otherwise we execute the silk for will guarantee that we spread out the iterations of this for loop onto different threads. And then we have to specify that the sum here is a special reducer operation that we can get the result from here. So don't worry if you don't follow me here. I just want to point out that we can do the threading and we can do vectorization with a very simple notation here. Even simpler notation is with OpenMP, but that's only for threading, not vectorization here. There is a notation for vectorization, but it's the combination of vectorization and threading with OpenMP is not that obvious. So with OpenMP, we keep the sequential code completely intact. We only have to specify that we want to execute this for loop in parallel, and that it is a for loop, and that sum is a reduction variable. That's all. That's all to it. It will do what it takes to thread this code, make sure the iterations execute on different threads, and also make sure that the result is correct by specifying that the sum is a reduction variable, which we reduce over. Note that we did not specify either with Silk or with OpenMP the number of threads. That's controlled by a different manner. So the code is completely portable for different processors. At the runtime, it will select the number of threads that is suitable, or as you specify when starting the program. So to conclude, explicit parallelism is a requirement for scaling. Moore's law is still in force. We get more and more transistors. It's only about transistor density, not about scalar performance. Patterns are a structured way to think about applications and programming models. It's useful for communicating and understanding structure. It's useful for achieving a scalable and portable implementation. High-level programming models do support scalable parallel patterns. They take care of the parallelism, data locality, determinism. There are low overhead implementations. And for most of the rest of the course, we're going to talk about how these high-level programming models work, how they are implemented, how they support certain patterns in a more detailed manner than what we have looked at now. And time for a quiz.